Oh, I have to say share, okay.
Maybe you can make it full screen. Do you have any audio or?
No, I don't have audio. I don't have movie, no
Okay.
audio, no movie, just plain slides.
Okay, okay.
So I think we should keep it that way, right?
It becomes easier, but in case you have, then we need to make sure that it is working properly before starting the webinar, right?
Yeah. No, I don't have any audio. I don't have any video. It's just plain slides in color. That's all.
Okay. Okay, so the plan is we will start at 10:30. I mean, we will start in another 10 minutes. And we have some of our attendees attending through the live session, which will be hosted in on Facebook and YouTube. We will have some panelist members here who are faculties in our institute. We will have a few attendees through Zoom, and the others will be watching live streaming. That's how it is. So we will have some 45 minutes talk followed by some Q&A. There is, do you see a Q&A chat?
Hold on for a second.
Okay.
I have to watch the time, so I'm going to get my phone here. Okay. And Q&A. Let's see.
Yes, so I was saying that there's a Q&A chat icon, if you can see on the screen next to share screen.
Well, now I only see, okay.
Because this is in full
oh yeah,
screen.
I see it. I see it. Yes.
Yes. So maybe some of the attendees might post questions here, which we can take towards the end of the talk.
Yeah. Will you monitor this
Yes.
this question, because I don't think I'll be able to do that during my talk. Thank you.
I can all.
The connection is bad. I don't hear you anymore. Hello? The connection is bad. I don't hear you anymore. Hello? There is a music in the background, but I don't hear you, Professor. And the screen is frozen on your side. I'm going to stop sharing, okay? I think the connection is lost. Hello?
Hello?
I see Professor Singh, but I don't see Professor Yadav anymore.
She might have some network issues, I think, from her side.
Okay. Oh, so you are back, okay? Professor Yadav, we missed you.
Oh, okay, can you hear me now?
Yes, I can see you and I can hear you.
Okay, so I was saying maybe towards the end of the session, I can dictate questions to you so that you can answer comfortably.
Okay. So you will read the questions for me, right?
Yes, yes.
I don't know what happened. I don't know why this connection froze. We have to say it's really far away. It's halfway across the globe.
Yes,
so
it
it's
is.
Amazing that it actually
From
works.
the two parts of the world. Correct.
I know.
Are you enjoying working from home these days, or do you miss going back to the university?
Well, it's a mixed feeling because I used to travel a lot.
Okay.
And so honestly, I think it's good to be home for a while. But what I don't like is the lack of social interactions. Like I saw some friends today and we had to sit like 2 meters apart. It's not the same. But I have a lot of email messages, a lot of WebEx meetings. So a lot of meetings are now online, and it's really not the same as in person.
Yes,
I'm very active in IEEE, and we had a lot of in-person meetings. So from one side, it's good not to travel anymore so much, but then the meetings do not have the same dynamics. It's very different. The discussion is different.
Yes, it is. Not everything gets communicated through online medium, so we do have that loss in while working online.
Yeah. Now,
we are also,
when I travel, go ahead.
Yeah, please go on.
When I travel and I take the, sorry. Mike, I'm giving a talk and I'm talking to people in India. So maybe you can call me in 1 hour or tomorrow. Thanks. Bye. Bye. Sorry, I hope nobody calls during my call. So it's different because when you travel for the meeting, you are at the meeting, everything else stops. You don't have to reply to email. But now when you're home, everybody expects that you are constantly connected, like the phone call that just came, right? So.
True. That's the same happening with us too. We are also working, taking meetings online and taking lectures online, trying to take even exams online. So now everything has shifted to an online medium.
Yes. Yeah, we did the same.
We still hope that this situation ends soon and we are back to going to university and taking lectures and our work. I mean, our work, if possibly, we can do in an offline mode, like the way it was earlier.
Yeah, different feeling. So when you are teaching online, it's in synchronous mode. That means the students have to attend at that time, and the lecture is done online, but at that time, because some universities are thinking about recording the lectures, and then you do it in asynchronous mode, which I don't think it's a good idea.
We are doing it in a synchronous mode, but still there is, some kind of loss because we are not able to understand, because we are not able to look at expressions of the students concurrently. So we do not really understand if they are getting the thing, or do we need to explain, or it has to be, talked about during synchronous teaching like this in an online mode. So it is challenging, but still there is a solution to it.
Yeah, well, this is how it is, and that's the best we can do.
Yeah.
But it's a serious pandemic, I think. We have never seen anything like this in my lifetime.
Yeah.
So the most important thing is to stay safe and healthy.
True.
So I don't see Professor Dutta. How do you pronounce his last name? Dutta or Dutta? Dutta? Professor Siga can see you, but Professor Yadav has disappeared. So
we can pronounce him Professor M.K. Datta. D-U-T-T, Datta.
I know how to spell it, but I don't know how to pronounce it. So it's Datta.
He may be in meeting, ma'am, during the talk. We will proceed. He'll join soon.
We can proceed?
Yes, we will proceed. He will join soon.
Okay. But I see Professor Yadav disappeared. I mean, she's there, but it's just a photo. I think we lost her. Oh, here is Professor Datta. Hello?
Hello, can you see me and can you hear me?
I can see you and I can hear you.
Okay, great. So Thank you, Professor Ljiljana, for your interest and coming up with this talk. So great seeing you once again. So what I see is I can see you properly, but there is some sort of a lighting problem. I mean, your face is little dark. I mean,
Because I only have a light in my room, which is on the ceiling.
oh,
And
okay.
so the light on my screen is the best I can do.
Okay, okay. But
I don't
anyway,
have a that lighting. That lamp doesn't work, unfortunately. The bulb died.
but anyway, it's pretty clear, and the voice is also clear. Did Brinda, did you join? Is Brinda here?
Yes, she has joined, but again, she has again facing some network issues today.
So maybe within 1 or 2 minutes time, we should start.
Okay.
First, somebody has to introduce the speaker to the audience, and then we will start within 1 or 2 minutes. So Professor Ljiljana, this is, you will have some maybe 7 to 10 people in this panel, and rest of this talk will be live streamed to our students who are in their own native places. It's a big state here, so they will be logging into the live stream. So they won't be directly in this panel. So in this panel there will be around 10 people who will be there, and rest your talk will be live streamed. I think that's the modality. So
That's fine.
Brinda, did you join?
Yes,
No,
yes, I did.
She did.
So
Okay.
Brinda, we can start.
I
I think
got
it is
disconnected in between, but yes, so we will start in no time.
so I'll request you is there a Divyanshu? Is the live stream on?
It is already started.
Yes,
Sir.
it is on.
Divyanshu?
Yes, sir. Live stream is on, sir.
Okay, so Brinda, you can introduce the speaker and we can start.
Okay. On behalf of Center for Advanced Studies, I welcome everybody to this weekly webinar series, which we organize every week. We have Professor Ljiljana Trajkovic from Canada today as a speaker. She received Diploma Engineering degree from University of Pristina in 1974, MSc degrees in Electrical Engineering and Computer Engineering from Syracuse University in 1979 and 81 respectively, and also PhD degree in Electrical Engineering from University of Canada in 1986. She is a professor in School of Engineering Science at Simon Fraser University, Canada. From 95 to 97, she was National Science Foundation Visiting Professor in Electrical Engineering and Computer Department, University of California, Berkeley. She was a research scientist at Bell Communications Research from 1990 to 97 and member of technical staff at AT&T Bell Labs from 1988 to 90. Her research interests include high-performance communication networks, control of communication systems, computer-aided circuit analysis and design, and theory of nonlinear circuits and dynamical systems. She serves as IEEE Division X Delegate Director 2019-20, and she has previously served as Senior Past President of IEEE Systems Man and Cybernetics Society 2018-19. She is chair of various prestigious IEEE conferences and an editor of various prestigious IEEE journals. She is also a distinguished lecturer of IEEE Systems Man and Cybernetics Society 2020-21 and a professional member of IEEE HKN and a life fellow of IEEE. We very warmly welcome you, Professor Trajkovic, and we are looking forward to hearing from you. Over to you, ma'am.
Thank you very much, Professor Yadav. I would like to thank Professor Datta for inviting me. I came to India in 2015, and that was really my first and the only time that I physically was present in the country. So I'm very glad that I could give a talk and at least virtually visit India again. So, so thank you very much for giving me this opportunity. I'm going to share the screen now, and I'm going to start with my slides. So I'll be talking about complex networks. It's really a very wide field, and I'm going to put the topic in the context of my research that I have been doing with my graduate studies at Simon Fraser University, which is related to computer networks. So it's really related to application of machine learning to understanding the traffic that we see in the internet. And we are very much interested in trying to figure out the anomalies and viruses and blackouts and ransomware. And we can get that information from the traffic that we can collect. So in my view, the complex networks within the topic of my research is really related to computer networks. So I have a lab at Simon Fraser University. It's called Communication Networks Laboratory, and we put a lot of material online, and it's free for download. And we always look for collaborations or some ways of connecting with the international community. And many of the talks and the slides and these slides will be posted eventually online. So this is the website for my lab. And as I mentioned, Simon Fraser University has several campuses. I'm on the campus in Burnaby in British Columbia. So this is the campus. This is how it looks like on a sunny day. As I mentioned, we have 3 campuses. This is the main one and the oldest one. And in 2015, we celebrated 50 years. So it's relatively a young university. And it probably doesn't look like the photo because we have a lot of constructions going on. Let me introduce the topic. So I'll introduce the area. I'll talk about the data processing that we do, machine learning models that we develop, experimental procedures, and of course, the performance evaluation of the algorithms that we use. And then I will conclude and I'll provide some references for people who are interested in the topic. So let me talk first about the complex networks. Don't get scared. The slide is very busy. But what the slide shows is actually the development of what we call complexity sciences. So you can see on the top the historical trend from 1940 all the way to 2020. And you can see different colors indicating that we talk about dynamical system theory, system science, artificial intelligence, cybernetics, and how these all fields developed over the last 80 years, and the major contributions. So you can also see that the major contributors in the area of research and development. And the credit is given to Durham University, to Professor Brian Castellani, who actually came with this graph. And it's interesting to see how many different engineering and scientific topics are actually connected to with what we call complexity science. And nowadays, we are very much interested in machine learning and artificial intelligence. And you can see on the bottom of the screen that artificial intelligence as a topic actually came in 40s. And it was very popular in the 90s. And then there was a little gap. And there is a history about that, why people stopped being interested in AI in the 90s. And the reason is because the funding stopped. And then with the advent of GPUs and fast computing systems, now the AI is blooming again, and we are talking about machine learning as a part of artificial intelligence. So let me mention the internet as one of the complex systems. And this is a very nice view. All of these photos are publicly available. I'm giving a credit for the photos. And this is the view of the internet. This is how internet looks like when we look at it at the autonomous system level. And so autonomous system, it means a campus. So for example, your university would be just one dot on this graph. And it shows that the graph of the internet is very interesting. It is what we call scale-free network. There are graphs, there are nodes that are very connected. These are huge research and university centers. And there on the outside, you can see the nodes that are not that connected. And so this is what we call, from a statics graph point of view, a complex system called internet. And we see it as what we call a scale-free graph. So this is one example. So this is what the graph shows. It's a partial map of the internet that's based on the January 15 data. Each line is drawn between two nodes. They actually represent autonomous system addresses. The length of the lines is very important because it captures the delay between the two nodes. And as I mentioned, these are not computers, these are autonomous systems. These are huge centers that have a lot of local area networks inside. And graphs represent a certain percentage of certain classes of addresses. And the line, the colors in the graph are also important. They show various domains. For example, dark blue is .net, .california, .us, Canada. Green is .com and .org. Red is military and government. Yellow is various countries. So the graph represents the delays, the connectivity, and also the domains. There is another example of scale-free network, and this comes from Wikimedia webpage, and it's a graph that was generated by looking at metadata of thousands of documents that document social network of hundreds of League of Nations personnel, and Professor Ljiljana was responsible for creating the graph. And I'm showing you all these graphs to sort of explain the complexity and the connectivity of various graphs that we can create. And as I mentioned, I'm specifically interested in viewing the internet as a complex network. So that's a little bit about the system that we are trying to analyze. And of course, we look at the various machine learning algorithms, and there are a variety of those. And we use machine learning techniques to detect network intrusions. And that's really a very important topic in cybersecurity. And you probably often hear on the news that these days, the ransomware is a very hot topic, where the organizations are kept captive to the ransom, and until they pay, they cannot get their data. So it happens as we speak. Machine learning algorithms have been used to successfully classify network anomalies and intrusions. And these days, we are concentrating on using supervised machine learning algorithms. So there is still a very interesting open research area to work with semi-supervised and unsupervised machine learning algorithms. And it's probably the future of machine learning algorithms. We experimented with the classical machine learning algorithms, such as support vector machines. But more recently, we got very interested in long short-term memory, gated recurrent unit, and very recently, broad learning systems. And so these are the algorithms that we use with the data that we either collect or we download from research sites in order to detect anomalies. Data are very important, and it's not very easy to collect the data that are good and useful for this kind of research. So we rely both on our own collection and the collection of data that's available to the research community for free from various sites. So today I'm going to talk about Border Gateway Protocol datasets. Border Gateway Protocol is de facto industry standard for routing the messages. It runs on top of TCP. So every time you send email, you actually use Border Gateway Protocol as a routing protocol between various autonomous systems. And that's a protocol that enables the data, the messages, the video, in order to be transmitted from the source to destination. We also experimented with datasets from a KDD dataset from University of Irvine. NSL KDD is a newer version, and we looked at those data in order. They also have not only images, they have data from networks, and we use that data in order to compare various machine learning algorithms. And more recently, some of these data, BGP and NSL KDD, are quite old. So we looked at the data collected from Canadian sites in 2017 and 18 to see how these machine learning algorithms behave for newer data, because as we speak, internet changes, the applications change, the algorithms change, the number of users changes. So it's very interesting to look at more current data. So these are the data sets that we are going to analyze. And these are some gory details about these data sets. So they are going to be used to evaluate anomaly detection and intrusion techniques. BGP, there are two data sets. One is from RIPE, that's Réseau IP European, and the collection sites are in Europe. And we also looked at the route views data set more recently, not in this talk, but the route views data set is collected from at the University of Oregon. And we are talking about long periods of collections. We are talking about 10 to 15 years of daily collections. So we talk really about huge data sets. We also collected data from BCNet. BCNet stands for British Columbia Network. It provides services to all the universities in British Columbia, research hospitals, research institutions, and we were lucky to have a collaboration with them where we had our own equipment that's installed there, and we can collect the data. NSL-KDD is an improved version of KDD99, very much known in research community. It was used very much for image processing, and it's also used in various intrusion detection systems that were built in order to detect anomalies. More details about 2017 and 2019 data sets. They're actually created from testbeds. These testbeds were used to create publicly available data sets that include multiple types of recent cyber attacks. And usually when we talk about data sets, it's very important to provide information. When were these data sets collected? So this was the network traffic was collected on Monday, Friday, and Wednesday, and another Friday in March and July of 2017, and then in February and March of 2018. So we are talking about more current data sets. This is how we do analysis. We usually look at the day of the attack, and some of these attacks are very well known. I'm going to mention some of them. You can see them on the slide. Code Red 1, Nimda, and Slammer were very well known worms and attacks that happened quite a long time ago, but they took internet down for a prolonged period of times. So well-known data centers were down, like Yahoo.com, NewYorkTimes.com, and that very much affected many companies who rely on e-commerce. So we usually look at the date of the attack, and we look at the 2 days before and 2 days after in order to have enough data to do the good training of the machine learning algorithm. And then we use the testing phase in order to be able to detect the anomalies. So this is how we collect the data, or we download the data. This is a period of time that we look at. And then we look at various features of the protocols that are used. So we look at 37 numerical features that are part of the border gateway update messages. And we've experimented with a variety of percentages used in order to do training and test. So now for our data, for our analysis, taking 60% of the data for training and 40% for test provide the best results. Usually in engineering approach, we talk about 80-20, but for our data, it turns out that 60-40 was a good division, because it really depends not only on the algorithm, but on the data that's used. On the bottom of the slide, you can see the gory details about 3 worms that are quite known in the history of internet, Code Red 1, Nimda, and Slammer. You can see that we take over 6,500 minutes of regular data, 600 anomaly data, and we used certain percentage for training, certain percentage for anomaly, and we also do the same for Nimda and Slammer. Okay. For the KDD, NSL-KDD data sets, these are the data that we use. You can see that it's a much larger data set. We use KDD Train Plus as one of the data sets that's available. These are all available to research communities. We talk about much larger data sets. And currently we are working on a new project. So we talk about gigabytes of data these days. Okay. These are the types of intrusion attacks from 2017 data set. You can see now we can talk very specifically about kind of attacks that happened 2 years ago. We talk about brute force, heartbleed. They all have very interesting names. And these are all hackers who were actually trying to take the internet down. And we also have certain labels. You can see this is FTP or SSH for those people who know about network protocols and the kind of scanning that can be done. For the 2017 data sets, number of features, right? We talk about flaws actually in TCP language, these are the connections. So you can see that we talk about quite a large number of flows. On Monday, for example, we talk about 500,000 flows that we analyze. Just to give you some feel about the size of data that we use. And in my lab, we use a GPU in order to do processing because it's much faster. And machine learning really came to be very popular because of the GPUs and the sheer power, computing power that we have today, so that you can have neural networks with thousands of layers. These things were not possible 20 years ago. More details about 2018 data sets. The collection is that I'm showing is in February and March of 2018. And these are gory details about kind of attacks. And you can see a lot of DDoS attacks. This stands for denial of service and distributed denial of service attacks, just to give you hardcore about the data that we did. So that's a lot about the data. An important part of our research is also dealing with machine learning models, right? These days, very hot topic is deep learning, and we have been using multi-layer recurrent neural networks. We call them RNNs, and these are the networks that we are going to use in order to train and test the network. So this is, for example, one deep learning neural network. You can see on the left-hand side the input layer. We have a recurrent neural network in the other layer. We have fully connected hidden layers, and then on the right-hand side, there is output layer. How many of these layers? We have experimented with a variety in order to get the best performance. So for example, when we analyze BGP data sets, we use 37 recurrent neural networks. When we analyze NSL-KTD, we use 109. In terms of hidden layers, in all cases for both data sets, we use 80 in the first level, 32 in the second level, and 16 in the third level, fully connected hidden nodes. So that's one of the deep learning neural networks that we experiment with. It's a higher view. We worked with the long short-term memory as one of the RNN networks. This shows you the higher view of the repeated module for LSTM neural network. On the right-hand side, we have a previous step with the input, various functions in between, and we have the output. And this is how these LSTM cells are stacked between input and the output, and you can have many of these cells inside. So this is LSTM. It was introduced a long time ago. It became very popular these days. This is the math. I usually put this slide just to tell you there is a very nice fundamental mathematical theory behind. We sometimes forget about it. Very often students will just try to run various codes that are very freely available on the net, usually written in Python, but there is a math behind. So that math is very interesting, for example, for people who work in control theory. Why do these systems work? And the big question is, why do they converge? So there is a lot of interest in the control system theory groups to find out how do we get the fixed points of this mathematical model. So it's not really just trying. Fundamental understanding why these models work lies behind understanding the mathematical models and understanding the process behind. So I usually tell my students, don't just try to run the code, and it's not a trial and error, there is a math behind. Okay, so this is finally the output of the cell that we can calculate using all these functions. And I don't really expect you to understand all of this. It's just really for the record, there is a nice, fine mathematical theory behind the deep neural networks. This is another unit that we use. It's also a recurrent neural network. It's gated recurrent unit. And it's a slight modification of LSTM. And it's a little bit simplified, but sometimes it performs very well. And it's one of the nodes in the RNN networks that we are going to use. And that's a math behind, very similar, but as I say, GRUs are a little bit simplified from LSTMs, and we use them. And probably the novelty in my talk today is addressing what we call broad learning system. The proposal for the algorithms came in early 2017, and it came from a group in Macau, University of Macau. It was led by Professor Philip Chen. In the meantime, he moved to South China University of Technology in Guangzhou. So he's now in China. But he came up with a very interesting idea. His idea was, why do we have to go so deep? Is it really the depth of the neural network that provides a good performance when we do testing? Why don't we go broad? We can build a network not going deep, but going broad. And so that's one of the algorithms that came recently. Most of the publications were done in 2019 or early to this year. And it's a very interesting model. And it worked very well for us. And I'll tell you why it works well, right? So there is a computational effort. There is always a price to pay. But something nice about this broad learning system is that they are very fast. And the speed is very important when you want to detect network anomalies. You want to detect them online. You want to detect these worms and attacks and ransomwares as they happen in order to take the routers down and shut the attack down. So that's why the speed is important. And this is the idea. These broad learning systems, instead of going deep, they're actually going broad. So you can see the set of nodes called mapped features. You can expand them if you want a better performance. There are enhancement nodes. You can also expand them. There is input on the bottom. You can play with the input. If the performance is not good, you can always add additional input data without a need to recalculate all the coefficients in the network. So it's a very interesting approach, and it's called broad learning system or BLS system. When we talk about increments of features, increments of network or nodes, and also incremental data that can be added inside the process in order to improve the performance. So that's something that we have done. So this is the mathematical background behind. I'm going to post all the screens on the web so people who are interested can actually look at them in gory details. Just to tell you, one of the reasons why this system works well is because they use a pseudo inverse. They don't use backpropagation as in other neural network algorithms. And that's really very much speeds up the process. And we call this original BLS. This is how it was proposed. But there are all sorts of extensions. There are many variants of this BLS. So for example, RBF function is implemented using Gaussian and weighted vectors. You can do cascades of math features. So this is the idea, not to go only broad and flat, but to add another dimension, something similar to deep learning networks, but you don't have to go to so many layers. So you can see, for example, that you can do cascades of math features. So these are the features. This is the broad learning system original on the bottom, and then you can do the math features and cascade them. Or this is, we call this a modification of BLS, CFBLS, and there is an algorithm how to do the cascades. One can do cascades on enhancement nodes. You can see the nodes on the right-hand side. They can be also cascaded, and they can be generated from features, or you can do both. So there is a variety of modification of these broad learning systems in terms of functions we use, or how do we structure this broad learning system by introducing a little bit of depth, and we call those cascades. Okay. So this is about the background. So it's about the system. We look at the internet. We look at the internet at the autonomous system level. We look at the border gateway protocol as a routing protocol. We look at elements of the BGP protocol. So we look at announcements, and we collect these announcement data from various sites. So I mentioned the data sets, and then I also mentioned the algorithm that we are going to experiment. And especially in this lecture, I'm concentrating on broad learning system as one of the novel learning algorithms that are becoming very popular in a variety of engineering and scientific fields. So now I would like to tell you about experimental procedures. So until now it was a background. So I want to mention experimental procedure. This is the intrusion detection system that we have been building in my lab. So it's a software system. So you can see data sets on the right-hand side. We do the partitioning of data sets. We, of course, divide it into training and test. We do the data processing. We have to convert all the features into numerical features. We also experimented a lot with feature selections. So in some of these algorithms, the feature selection is not explicitly a step anymore. But it's very important to understand that selecting features and combination of features is going to greatly affect the performance of your algorithms. And for example, in SVM, you specifically have to select the features in support vector machines. But in some of the new algorithms, these features are somehow hidden. But understanding which features are selected and which features play important role in performance of the algorithms is rather important. And of course, we do normalization. On the right-hand side, you have the training on the top and testing on the bottom. ML stands for machine learning algorithms, and I mentioned several that we use. We do a 10-fold cross-validation, and of course, the tuning of parameters. So there is a lot of work in place in order to do the testing, in order to tune the parameters, in order to improve the performance. Okay? And then at the end, we do classification. In our vocabulary, classification means if you give me data points, I should be able to tell you whether it is anomaly, whether it's intrusion, ransomware, or blackout, and that's what we call classification. This is the experimental procedure. So we normalize and train the data set. We train, in this talk, I'm talking about recurrent neural networks. We train the models. We also experimented with broad learning system, 10 cross-validation, tuning of the parameters, and then after the training, we do the test. And we did the test with both sets of machine learning tools. And then we are going to use two performance metrics, accuracy and F-score. You can use other matrices. There are other matrices that can be used, like sensitivity, a variety of those. But in this talk, I'm going to talk about performance using accuracy and F-score. Okay. As I mentioned, in order to make your algorithms work well, one really has to understand the physical system behind. So this, for example, what we plotted are the most relevant features in 2017 data set. And you can see that not all features are equally important. And of course, in your study, you would like to concentrate on features that are most relevant. So for example, average packet size was very important. Some of the protocol that's used is important. Destination port is very important. So if you can work, if you work with the entire set of 37 features, it's a lot of work. And some of the features really do not affect the performance. So you want to concentrate on selecting the most relevant features. So we sort of plotted in 2018, for example, the most relevant feature was the forwarded segment, minimum forwarded segment size. And you can see that, for example, on the right-hand side, these features are not that important because it really depends on the data. So these are the training parameters that we choose. So for example, for BLS, we choose for 3 different worms, CodeRed1, IMDA, and SLAMR. We choose 100 map features for CodeRed1, 500 map features for IMDA, 100 map features for SLAMR, and for NSLKDD, I think it was 100. I don't see it on the slide. These are the details about the model. Let me go back, I'm sorry. Just to give you a feel about what is the number of features that we talk about. So we talk about hundreds of features that mapped features. These are not features of BGP. These are mapped features in the BLS, flat structure, okay? And so these are the details. Because I very much believe in reproducible research results. That means whenever we present results, we really try to give all the gory details about the models that we create. So these are the BLS training parameters. And this is for 2017 and 2018, because sometimes the criticism of working with old data is the data is old, the system has changed. And this is why we have moved in 2017 and 2018. And you see the models that we use. We used a smaller number of features because the data set was much larger. So we didn't have to use so many features. So you can see order of magnitudes, fewer features that we are using when we are dealing with 2017 and 2018 data sets, but they are much, much larger than the worms that we presented before. This is for incremental BLS, right? And so we talk about different number of features. We experimented with 78, 64, 32. The more features you use, the more work you have to do. The algorithms are slower, it takes longer time. So you would like to select a number of features that are optimal in a sense to give you results in a reasonable time. So that's about procedures. And I would like now to talk about performance evaluation, to tell you a little bit about what's accuracy and F-score that we can achieve with this kind of models. And one important aspect is also the time that it takes. And as I mentioned, in order to detect anomalies, it's very important to have algorithms that are very fast. So, sorry, I'm not supposed to touch the screen very much. So this is the data set, BGP, where we are looking at the SLAMA only, and the NSL-KDD data set. And these are different models, like how many, this is LSTM2 and LSTM3, okay? These are different models that we created with different layers, like LSTM2 with 2 layers, 3 layers, 4 layers. These are GRU models. We use the Python, both on CPU and GPU. And in this slide, we are collecting, displaying the data for SLAMA and for NSL-KDD, right? And this is the time that is needed to do the training. Test, usually people don't report how long it takes to do the test, right? And I'm sorry, people usually don't report the training, but in this case we did, to show you that it takes a long time in terms of seconds to do the training, even if you do GPU, right? And this is on top is CPU, on the bottom is GPU, and of course we are talking about order of magnitude different because the graphical processing unit are much faster and of course much more expensive. This is the BLS model, and you could see something very interesting, right? Order of magnitude decrease in terms of time that is needed to do the training. And that's the most important advantage of BLS models. They are very fast. And you probably would wonder, are they accurate enough? And interestingly enough, their performance is relatively good compared to other models, but the time is much faster. So even if we use CPU, you can see we talk about 21 seconds or 9 seconds, and that's 10 times better, order of magnitude better than the RNN models. Okay. These are the LST models for BGP datasets. We are talking about now about performance in terms of accuracy and F-score. So for example, these are the 3 cells that we use, 3 models that we created using LSTM model. We talk about accuracy in 94%. Of course, we talk about accuracy in terms of test because that's the most important. You do the training in order to get parameters, and then the test shows whether the algorithm works nice or not. So these are the accuracies that we could achieve. And I think in red, it's the best accuracy, and it shows that that's a model LSTM2. This is also a good model for LSTM4. We talk about accuracy and F-score. So for example, sometimes you can get a good accuracy, sometimes you can get a better F-score. RAP regular was a data set that we downloaded from a website. It doesn't have any anomalies, and BCNet was the data that we collected. And you can see we are working with anomalies. So of course, it's not very easy to detect the regular data because the goal of this research study was to detect anomalies, not the regular data. And this is the GRU model. You can see a comparable performance. The model is a little bit simpler, okay? And this is the BLS model. And I would like to point out that even though the model is much simpler, much faster, right? You can still achieve the good accuracy and good F-score, comparable performance to other models. And that's the advantage of using the BLS. And some more gory details about various cascades. C stands for cascades. So we don't use only the flat model. We try to build a little bit, but a couple of cascades. So these are cascades of features, cascades of enhancement nodes, cascades of both. And of course, the accuracy is a little bit better and F-score is better, but the price to pay is the computational complexity. So this is now about NSL-KDD dataset, the models that we used. We experimented with data sets that are very much common in a research community. So we use the 3 data sets, test plus, test minus 21 is a specific test that turned out to be difficult to test. And this is accuracy and F-score. Okay. And this is for 2017 and 18, just to get a feel that we are talking about accuracy and F-score that are more than 95%. Okay. And these are the performance graphical display. We talk about accuracy and F-score. This is the number of selected features. And of course, the more features you use, the better accuracy and F-score, but sometimes it doesn't pay off, because if you work with 78 features, you have to spend a lot of time and a lot of CPU cycles in order to do that. And you can see, for example, for BLS model, the number of features doesn't really affect that much the performance and accuracy. BLS model is in blue, okay? And incremental BLS is in red. Incremental means if I'm not happy with accuracy, I can increase the number of input data. This is why we call it incremental. It's a modification. And you can see that accuracy and F-score are much better. Training time, of course, training time is going to increase if you increase the number of features. And you can see that it's increasing from 65 to the training time increases. You can see it on the right-hand side. Sorry, accuracy is on the left and the training time is on the right. So it can increase from 9 to 15 if you do the plain BLS, and you can see the increase in time with respect to the number of features you use. Okay, and this is also for 2018. Sometimes there are dips that we cannot explain, right? It really depends on the data, it depends on the models and parameters. So I would like to come to the conclusion to sort of give you a summary of what I talked about today. It's evening in BC, but I understand it's morning in India. So we evaluated the variety of machine learning algorithms. We concentrated on LSTM and GRU, deep recurrent neural networks. These are 2 variants of RNNs. And we played with a variety of hidden layers. So when we talk about LSTM2, LSTM3, LSTM4, we talk about having 2 hidden layers, 3 hidden layers, or 4 hidden layers. And then I talked in more details about broad learning system models. They use a radial basis function as one of the functions of choice. We also talk about flat BLS. We talk about cascades of both map features, enhancement nodes, and also we talked about incremental learning, when you can add the data in order to improve the performance of the algorithm without recalculating all the parameters. And that's one of the nice features of BLS. So BLS and cascade combinations of map features and enhancement nodes achieve comparable performance, but had much shorter training times. Why? Because of the wide and deep structure. So the BLS models consist of small number of hidden layers, and they can adjust weights using not backpropagation, but pseudo-inverse. And this is why, or Penrose, pseudo-inverse of matrices, and this is why they are much faster. Then the advantage is also to be able to dynamically update weights in case of incremental learning. You don't have to recalculate all the weights. You dynamically update them. And these better optimized weights are due to additional data points for large data sets. The larger the data sets, the more data you of course, you have, and you can better optimize the weights. Of course, there is always a price to pay. While increasing the number of map features and enhancement nodes, as well as mapped groups, provides better performance. Of course, it requires additional memory and training time, and that's the price to pay, right, in terms of using the BLS. So usually in my talks, I also give a credit to the sources that I have used. So BCNet, as I mentioned, is an organization in British Columbia. We have a collaboration, and this is the website. We have a measuring device there. RIPE raw data is publicly available to research community. They have been collected data for last 15 years. There are daily collections. Of course, it takes time to download and resources and to manipulate the data. I didn't mention in this talk route views, but we're also working with route views data from University of Oregon. And SLKDD data set is a quite known data set. It has been around in the research community, especially in people who do image processing, but there are also data for network intrusions. And 2 newer data sets come from Canadian websites. We use Python, Pandas, PyTorch. I mean, I think most of the people these days use Python. And I want to give a credit to the Broad Learning website with Broad Learning Systems. And some code is available. We also have our own code that we posted on our webpage in the meantime. And I don't have it here, but if anybody is interested, I can give you the link. It can be found from my webpage also. I usually put references for people who are new to the field and who might want to get involved in research, or at least interested in taking courses. So these are the main references about anomaly detection and about cybersecurity, deep learning, and network, all related to network intrusion. References on deep learning, these are the references we use. Of course, Jeff Hinton and his group, he's one of the 3 recipients of the HCM Turing Award for deep learning. And so these are with Hinton and Beggio. And these are the data that the references that we use for our deep learning system. Broad learning, I have put the references, early references, as I mentioned. The introduction was in early 2017. And then in IEEE transaction rural networks, there were 2 papers in 2019 and 2020 that describe the system. I think in the meantime, there were more publications that came out of it. We also have our own publications related to this work. I think the first publication we had was in 2012 with a small project that we started in terms of using machine learning for network anomalies. And we also had 2 book chapters. So if you're interested, sometimes conference papers are too short, too difficult to digest because we try to cram everything into a certain number of pages. But we have 2 book chapters. The first one deals with data. The second deals with machine learning algorithms that we use at that time. And they appeared in a Springer version, series, and the book was entitled Cyber Threat Intelligence. So we described at that time what the current status of research in my lab was. We also have some recent conference publications. We had another one in this year, but the conference was postponed because of the pandemic. So I have only listed those. I think we already posted it on the webpage. But this is work with my grad students. Many of my students are master degree students. Some of them are PhDs. But in this work, for example, the first author is Gilles Dali. He's my PhD student. Ana Gonzalez Rios is my master degree student. John Shu was a visitor, undergraduate student. So I involve all of them. And usually if something comes out of the research, we do publish it. So all of these publications are available from our website, PDF files. You don't need to log in, it's all publicly available. And I just want to end with the usual view of the internet. This is an old view of the internet. It comes from CAIDA. It's a research organization associated with University of San Diego in California. They have these beautiful, they had a group that worked on graphical displays of the graphs of the internet. So for example, this is a view of the internet, autonomous system level. I think it's already quite old, but it shows you very interesting structure of internet as viewed as a complex system with over 500,000 nodes and over 600,000 links. And you can see a beautiful structure, statical view of the internet as a complex system. So I think with that, I would like to end my talk, and I would like to thank you for listening to me.
Okay, so thank you, Professor Ljiljana. It was very nice. The video quality and the audio, the video and the audio quality was very nice. I think Brinda, can you hear me?
I can hear you.
Yes, thank you very much.
Brinda, can you hear me? Brinda?
Yes.
Is there
yes,
any?
I can hear you. Yes.
Is there any question from the guys who are in this panel?
I can stop sharing the screen,
There
and
is
I think,
one
oh yeah, I
question.
see the question.
Yes, yes, yes.
Okay, so I see the question. So the question is, what do you mean by broadens in BLS? Can you please elaborate? What I mean by broad learning system is that it's not deep. The layers do not go, floor by floor by floor, thousands of floors below. So it's not a deep structure, it's a broad structure. So in that broad structure, you can start with certain number of features and certain number of nodes. Let's say you select 50 features and 100 nodes. We are talking about features in terms of the BLS. And then if your performance is not good, you can add the features, you can add the nodes, you can add the input data. So you can broaden the structure. We talk about connectivity. So I hope I have answered your question in terms of what it means to broaden broad learning system. It means you add the feature nodes, you add the enhancement nodes, you can do the cascades if you want to go a little bit deep, but not thousands. We don't make 1,000 cascades, usually 5, 6, 10 cascades, because we want to take advantage of that structure that's broad in the two-dimensional space. I hope I answer your question. And the question was by Banoj Kaushik.
Okay, so anything else, Brinda? I think there is no other question at this moment. Okay, so Professor Ljiljana, also I would like to mention that currently we have established a center here in our university. The name of the center is Center for Advanced Studies. Can you hear me?
Yes.
So in the Center for Advanced Studies, we have a specialization of cybersecurity, and there are a few master students who are actually working, in malware identification using machine learning and deep learning models. So I think those students are in the live streaming model, so they're not in a position to ask questions. But in case if we have some nice, we have some publications also. So basically, we will maybe if in future I would like to share some of the results and maybe a couple of slides with you, the master students on which. And also we have some labs. We have some cyber physical systems labs. We put a lot of money in establishing those labs. So this is a very small sort of a research center that has come up where I'm working at the moment, and a very focused area. One of the focus is cybersecurity, and other focus is machine learning. So it's both the guys, a student from machine learning and a cybersecurity can always collaborate in finding a problem like malware identification, in the host level. Definitely. So there are some work. So at a right opportunity, I would like to discuss some collaboration.
That would be great. That would be great. I'm always open for suggestions. I collaborate with a lot of people. And I think with the new video and Zoom, and it's very easy to even have the meetings in,
So maybe once we have some results, maybe with you or maybe a couple of your students in Zoom and a couple of students from our side, we can have some 30-minute discussion at a suitable time.
Yes. And I think I have a student who is in Kazakhstan. She moved in February, and we usually meet around 9 o'clock in the PM. So this time is good. 10 o'clock is good. 9 o'clock PM is good. So I know it's morning for you. So it's doable. It's really doable.
Okay. So finally, on behalf of the institution, on behalf of our organization, I'd like to thank you for this wonderful talk, because listening to you is always amazing. The young minds, the young students will always be motivated, and they will find, they will be inspired to do some better work. So once again, thank you so much for your time and your interest coming down over here. We look forward to meeting you virtually or physically in real in future, and we also hope that the pandemic comes to an end soon. Ljiljana, can you stop sharing the screen?
Yes.
Okay, so some of our guys, some of our faculty are available right now here. So for the benefit of everyone, let me tell you, Professor Ljiljana, we had visited us in 2015 in Noida. So she, and I tell you, there is a huge fan following of our students who are following her in Facebook and and in other
Yes,
social media.
they are still there. I still have 50 students
Yeah,
from
and,
Hamid University, my friends on Facebook.
yeah, so there are a lot of students still they follow Professor Ljiljana, and she had won many hearts when on her visit to India in 2015. We hope
Lovely.
that once things gets normal and the virus and everything goes away, we definitely look forward to your visit once again to India. And having said
Thank
that,
you, Professor.
I thank you once again for this talk, and we close this online session. Thank you all the audience for listening, and thank you, Professor Ljiljana, once again.
Thank you very much. It has been a pleasure. Thank you. Stay safe and healthy.
Thank you, ma'am, for
same to you.
thank you.
Thank you.
Thank you, ma'am.
Bye.
for coming.
Thank you,
Thanks.
Professor. Thank you, Professor. Bye.
I think we can close the session.
Okay. Bye-bye. Bye, everybody. Thank you.
Bye, ma'am.
Bye-bye. Bye. Bye, Professor Yadav. Bye, Professor Dutta.
Bye.
Will please stop the YouTube live streaming.
Okay. Okay.
And close the session. Thank you so
Okay.
much.
Welcome. नेहा मुझे होस्ट बनाओ होस्ट नेहा होस्ट बनाओ जल्दी मीटिंग स्टार्ट होगी होस्ट बनाओ भाई नेहा से नहीं है अरे छोड़ो फिर मैं यहाँ से कर दे रहा हूँ रिसेट ठीक है हो गया